So welcome back all to today's final session of the conference. Looking forward to talks from Michael and Luis. First up, I'd like to welcome Dr. Michael Roberts, who is a Senior Research Associate of Applied Mathematics here at the university in the Department of Applied Mathematics and Theoretical Physics. He's also a member of the Cambridge Image Analysis Group and leads the algorithm development team for the global COVID-19 IX-CovNet collaboration. And he is also, if I understand correctly, a postdoctoral fellow at AstraZeneca in Cambridge. And today, Michael will present to us on the topic of lessons from the pandemic for machine learning and medical imaging. Michael, the floor is yours.
Does that come through all right?
Yes, that's
okay. Perfect. Yeah, so thanks for the invitation. I just asked to give an overview of our collaboration that's aiming to develop an open source tool for COVID diagnosis and prognosis, and then also some of the lessons that we've learned through doing this work and how we're working to not only develop the tools for doing this, but also to implement best practice for machine learning using medical imaging. And then also to look at preparedness for another pandemic. So how could we as a community have been more useful and fast off the ground using imaging and medical data, and how we could address that for next time. So the motivation for our collaboration is really when China got hit first with the pandemic, they were identifying features on the images that were quite specific for COVID. And this allowed them to triage patients at the hospitals. And so back in March of last year, a few of us kind of felt the moral obligation, knowing that there was going to be a lot of imaging coming out through the pandemic and a lot of associated clinical data. Could we use our skills to help in either diagnosis or prognosis of COVID from the imaging? So this is kind of the zoo of data that we have for COVID. So the overall question that we and lots of others asked is, can we apply image analysis, data analysis, and machine learning to try and extract those signals from the images or the clinical data and try and enhance the prognosis, the predictions for COVID-19 patients, and also to do rapid diagnosis? Because back at the start, testing was so limited that diagnosis from an image would have been much faster. And also, how can we best prepare for the next pandemic? So we have all this heterogeneous multimodal data recorded for every patient. And we're looking to see how can we integrate these different modalities, extracting features from each, and combine them into one tool that's of most use in the clinic. And the big aim for our collaboration is that we are going to implement this inside initially Addenbrooke's Hospital to really see, can we go from initial algorithm through to something clinically deployed? So this kind of is the same slide that Derek was showing earlier, which just shows the sort of breadth of our team. We can see we have a real nice balance between mathematicians, clinicians, image scientists, data scientists, statisticians, software engineers, all of us working together with the sole aim of accelerating the development of these tools, getting additional data, really understanding biases in the models, and what would be a most useful tool for clinicians when they want to implement it in the clinic. So this is kind of the timeline of how our collaboration evolved, to give some context for that. So back in March, there was a core group of investigators. We all met to say, okay, we really should do something. We think we can be of use in this pandemic. And we joined a EU-wide project at the time that was trying to get funding from the EU called Dragon. And then 2 months later, actually did get funded, which kind of led to the ballooning of our collaboration, and it's still going to this day. Actually within a month of starting the collaboration, we got our first data from China. because ironically, because China was hit first, they were also able to share data much faster than anyone else could. So we got data months before anywhere else from China. And we were able to start developing preliminary models and develop at least some architectures using that data. And we also released a literature review which considered all the chest X-ray models for COVID-19 at that time. And then through the summer, we started getting extra funding, approval of additional data sets, and approval in particular of the Cambridge data, where we have the electronic health record that records all of these detailed reads on every patient for temporally. So we can do a phenomenal amount of data analysis on that. And we also submitted a full systematic review, which I'll talk about later. And we then recruited 4 postdocs into both algorithm and clinical sites so that we have some longevity going forward. And we have a really nice balance as well with the clinical team informing the algorithm team and vice versa. And then towards the end of last year, we had the systematic review accepted. We added some extra teams to the collaboration from the US and Brazil. Postdocs started, and we contributed to an actual diagnosis algorithm for COVID. And then towards the start of this year, we found some preliminary results which indicated that there was a marker in the full blood count data that was taken in Cambridge that could have indicated the pandemic was hitting. So we saw these bizarre little spikes that were happening that potentially we were trying to isolate whether these surveillance studies could work, that we could isolate the pandemic. So we're working on that at the moment. And then the systematic review and some invited opinion pieces were published as well. And so in the last few months, we've continued developing the algorithms, and I'll talk about those later, but we're also participating now in a NHSX algorithm validation program to test one of the algorithms we developed on a completely external data set to see how it generalizes. So this is another slide that Derek showed earlier as well, but I'll just kind of take it maybe at a different tack. So back in April, there were lots of researchers wanted to help out. We all kind of felt an obligation to do something. We just didn't really know what it was. And that was kind of informed our decisions to really go slowly. So Julia Gogg published this article that was just saying about you really need to be amplifying the signal. And that's really the motivation of our collaboration. We're very keen on, rather than just publishing anything, we want to publish things that are really, really full of value and also have been validated a lot. And the same with the models that we publish and share. They will be validated quite a lot around different data sets around the world. And so taking this careful approach, we initially started to look out for what were the types of models that had already been developed or were being published around. And so they fall broadly into 2 groups. So we've got the diagnosis models, which are trying to identify COVID from an image. And so back in the sort of early part of last year, we had extremely limited testing capacity in the UK in particular, and there was a real hunger for a solution. And so there were lots and lots and lots of papers coming out that was claiming we can diagnose COVID from an image. This is much faster than a PCR. You should use imaging. And there were also lots and lots of public data sets being made available for COVID-19 imaging. But as well, it's quite unclear what is kind of your non-COVID-19 class, because a lot of people were using, and we'll talk about this later, but a lot of people were using, healthy patients as controls or unreasonable control groups to then compare to their COVID diagnosis, and developing quite peculiar models. And then there's also prognosis. So these are the models that predict the outcomes for the COVID-19 patients. So really predicting the outcome that you'll have. So in particular, death, ventilation, or deterioration of the patient. And this is where you run into problems where it's very rare to find linked imaging data to the outcome of the patient, or at least there's a lot of the data will be missing. And it's very unclear sometimes what the outcome definition is, like what is a useful outcome to predict for those patients. So many papers predicted completely different outcomes, and it's very unclear whether clinically those are useful definitions. And then it's extremely biased by the location of the imaging as well, so for example, if an ICU is overrun with patients that are far more likely to die versus an ICU that's far more relaxed and isn't under that level of pressure. And it's important to understand those biases. And then for prognosis, well, we also found there were very few papers at the time. And so we took, again, as part of this approach, quite a systematic view of the literature. We ran a review looking at all machine learning models that use chest X-ray or CT imaging for diagnosis or prognosis of COVID-19. And after screening 2,000 papers, we ended up with 320, which were satisfying this criteria. And this is for the 1st of January to the 3rd of October. And then we had a quality screening step here, which took us from 320 papers to 62 papers. And this was excluding papers for very, very basic reproducibility failures. So for example, if they didn't disclose where their data source, what the data source was, how they assigned data to different folds for train validation and test, if they were very unclear on their pre-processing, or didn't mention the pre-processing, or how they even selected the final model. So we can see that a significant number of papers didn't even clear the most basic of reproducibility tests. But then we got to 62 papers that we did a more thorough review on, and we found that none were of safe clinical utility, typically due to biases in the data, biases in the methodology for developing the model, the biases in the evaluation of the model led to this conclusion. And I'll just highlight some of the pitfalls that we found in a lot of the papers. So there was a real issue with data sourcing. So because the data was collected and uploaded in quite a panic, we found a lot of public data sets started to appear. And unfortunately, a lot of them were what we termed Frankenstein data sets, which were data sets that already existed being combined with, maybe some new data, maybe some existing data sets, and then being rebadged as a brand new data set. And so lots of the papers in the literature ended up training and testing inadvertently on the same data. So for example, if we look at this CERM data set, this fed into this IEEE data set as well as this radiography database. But then the IEEE also feeds into that one. And then COVID-X as a merger of these two as well. So this CERM data set has kind of moved around into all these data sets multiple times. And it leads to lots of duplication of images and images appearing in the train sets and the test sets quite frequently. And this level of duplication leads to far more optimistic performance than a model actually is achieving. And also there's a problem of appreciating the biases in your data. So in particular, say for the acquisition of the images, we have a huge number of papers that use a non-COVID pneumonia group to compare against their adult COVID group. But they don't mention that the non-COVID group is babies between 1 and 5. And a baby X-ray looks completely different to an adult's X-ray. So if you're designing a model that's detecting COVID versus non-COVID, in that case, you're developing an algorithm that will detect a baby versus an adult. And also there's issues with biases in the images themselves. So for example, if an image has a label, the algorithm can quite quickly learn to appreciate, for example, if we're doing a prognosis model and we're predicting whether this patient will have a good outcome or not, if the patient's already stood up versus lying down, it means they're already in a better position than the patient lying down who's unable to stand. And the algorithm can learn that from the labels. So we have erect and supine here as labels. And we can see that these saliency maps have learned that those labels are important for the outcome. Derek also talked about this, which is the incorporation bias issue. So I'm not going to run through it too much because he's mentioned it already, but the issue with incorporation bias where you label the outcome based on the image itself. For example, we look at this image and we say, is it COVID or non-COVID? The problem with that approach is that it hard codes in any of the biases of the radiologist at the time. And we really, really don't want this for a model. We would want the label to come completely externally, for example, from a PCR test. And then another issue is the resolution of images. So a CT, a chest X-ray image is normally thousands of pixels by thousands of pixels, but we almost exclusively find that people downsample the images, which is fine, but they're typically downsampled to say 224 pixels squared by 300 pixels square. And this is actually the resolution required for a lot of pre-trained networks. And so the data pre-processing step has been heavily influenced by not a clinical decision, but by the desire to use a pre-trained network. And this feels a very, very, very slippery slope to go down. So the kind of recommendations that we made in the paper were also, like, it's never been more important for a model to be, or a paper's findings to be reproducible than during the times of a pandemic. So we really were kind of insistent on reproducible manuscripts, code release, and model release, so that we could, if, you know, within a month of the pandemic starting, that someone shared a model that we could quickly validate on our data, it would have spared a lot of people independently developing models for diagnosis and prognosis. Also, holding ourselves to established standards. So out there, when we were reading these papers, we found it was kind of like the Wild West with the approaches taken to developing models. There was no consistency in the approaches, and there is some work on establishing baseline standards for the community to use. So there are claim checklists, for example, for deep learning models. There's a PROBAS checklist, which is around biases in your models. And I think these give a really good baseline for everyone to hold themselves to if you're developing a model for anything, but for COVID in particular. And then almost every paper, exclusively every paper, quotes its discrimination statistics about, you know, how well it can discriminate COVID from non-COVID, for example. But there's almost nothing about calibration out there. And it's absolutely crucial to understand whether the output of a model is a probability of an event happening, or whether it's just a number. So, for example, if we're predicting the probability that a patient will die, the probability being 60% coming out of the algorithm versus 90% will massively influence what a clinician will do in that event. So it's really important to not only talk about discrimination statistics, but massively about calibration statistics, and understand what the probabilities that come out of your algorithm actually mean. And the final part is to work collaboratively across disciplines. So many of the biases that we found were only identified by us working with clinicians. And also it's very important when we're talking about developing a tool for use in the clinic that we have them working kind of hand in hand with us to tell us what actually are the clinically useful questions and how would they interact with a tool. Like, it's very difficult to appreciate how simple this tool must be. It has to integrate seamlessly into the workflow. You can't kind of have any extra unnecessary clicks, and trying to think about how we can develop a model that's really, really going to be used. And the final thing is the great thing about having clinicians on board is the understanding of the dynamic questions. So as the collaborations evolve, for example, we now talk a lot about strains of the virus and how they affect things, and how whether the images look different or the outcomes for the patient are different. And strains were never talked about 6 months ago, but trying to appreciate those now and really understand how, you know, how can we incorporate that? What can we physically collect that can augment our models? So I just thought I'd show a little bit more about the collaboration. So this is about we spent a lot of time on data collection, so working with partners around the world to collect huge numbers of scans, which are COVID and non-COVID, and then label clinical data as well. And so we can see that, you know, by having sites in Europe, in Brazil, in America, and in China, it gives us a much more comfort in that the algorithm will generalize to a new population. And so these are like the 6 core themes that we identified for the collaboration. So the 2 main ones being the imaging themselves, so CT and chest X-ray, We also have one theme that looks at the longitudinal clinical data. And then moving away from the lungs, we have one project which looks at the heart features, in particular calcium scoring. So we know that COVID patients have much worse outcome if they have underlying cardiovascular issues, which we could identify from the heart itself. I'm working in particular on the full blood count, so studying the structure of the blood cells themselves and how they cluster in these, for example, these scatter plots, to understand, is there a difference between in prognosis for COVID patients dependent on the structure of their blood cells. So if your immune system is in overdrive and producing lots of brand new cells, can we pick that up from the full blood count, and can we infer anything about that from the patient? And the final thing is the quality control. So looking at, we get tens of thousands of images from lots of different sites, which is just physically impossible to quality check every single one. So developing a tool that will automate that QC process. I'll kind of give a summary about each kind of strand to this now. So for the CT project, so CT is a very, very rich modality, but it also leads to being incredibly difficult to work with sometimes because of its scale. But we've now segmented a huge number of CT scans into, for example, consolidation and ground glass features, and we can now understand, are there features of the ground glass or consolidation regions, in addition to just the severity or the disease burden, that can really indicate more subtle features that might link to the outcome for those patients. And similarly for chest X-ray, again, looking at the lungs of the patient, now we can segment out the labels that we were seeing earlier that can bias the model. Can we identify features of the chest X-ray which link to outcome? Also, chest X-rays are performed far more often in the UK. So we have a lot of chest X-rays in series where we consider the changes in the features of the X-ray over time and how that links to the outcome for the patients. Clinical data, so modeling, we're coming up with models which are looking at clinical data that's longitudinal. It has a lot of sparsity to it, so there's some readings only taken, say, once a day, where some are taken once an hour. We have a lot of missing data, so between two patients, some tests will be performed, some tests won't, and some readings will be taken and some readings won't. And so it's really important to understand that from the start, and how you can deal with missing data, because if a feature is very important for your model, how do you deal with it when it's not there? Biases as well. For example, if you're in ICU, your measurements will be taken very, very often, whereas if you're not in ICU, they'll be taken far less often. And if you're just learning that the frequency of a temperature measurement is very important for outcome, that's not particularly interesting. And then also the measurements are all non-equidistant as well, so we can't assume anything temporal about the data. And the other part to this project is then incorporating those imaging features into those clinical models. The work I mainly focus on is the full blood count. So it's the most common clinical test performed globally, 3.6 billion a year. And it's already used to come up with likely diagnoses for patients. You'll say whether they've got a viral or bacterial infection or a likely viral bacterial based on the full blood count. It's cheap, routine, and scalable. It's everywhere in the world. And our questions are, is there a viral signature in the full blood count? So could we have detected COVID from the blood straight away? Because that would be a very fast test that also scales around the world, because these machines already exist. The full blood count's already being performed on patients. Is there a COVID-19 signature as well as a viral signature? And then are there prognostic signatures as well? And the final part is the quality control. So automating the triage of these chest X-rays so we can much faster develop machine learning models. So when we get a kind of data dump of 20,000 chest X-rays, can we quickly exclude really poor quality ones? So here are just 6 examples from a data set we have, where in the top left, we have a good quality chest X-ray. Then we have some lateral images, some inverted images, under and overexposed chest X-rays, some that are scratched, and some that have pacemakers. A lot of COVID patients have pacemakers. So it's very important to either reject or accept images on the basis of this, but also to understand, if a model overperforms on the pacemaker group, is it just getting distracted by the pacemaker rather than features of the image itself? And so this is just the kind of the lessons for the flip side of the pandemic. So data availability, I think the main thing we found early on was a lot of people wanted to collaborate and wanted to work together, but they hit one of a few roadblocks. And the first being ethics can take a long, long time to get through a hospital, as well as drafting it in the first place. And then also, if they got the ethical approval, having the infrastructure to extract images and send them to us became incredibly difficult for a lot of sites. It either costs a lot of money or the facilities just don't exist to send the data. So I think focusing on that would be very useful. How are we going to develop the infrastructure, and how are we going to develop ethics proposals that could be approved much faster? Maybe a kind of boilerplate ethics where you insert the name of the disease later. A collection bias, again, like clinicians were the main people that were extracting images for us, but they were also the ones needed on the front line. So that causes a massive bottleneck where you get a bottleneck that you can't get to data because the clinical staff are doing their clinical jobs, but also you get biases in your data sets. It's the hospitals that have the flexibility to actually spend some time extracting the data tended to be the ones that got the data out there, where the ones that are really overworked wouldn't be able to share anything with us. So modeling as well. So when we have the data in our hands, how do we even do the modeling for this? And we need to have some approaches that are sort of pandemic specific, or that are able to take in a new class of disease without experiencing, say, catastrophic forgetting, and being able to say, okay, there's a new pandemic that's hit and we've collected our data really quickly. How do we very quickly develop a model based on that? And having those frameworks in place would be great. Missing data. So much of the data is incomplete because it's collected in a panic. And it really does vary across sites. The labeling, the certain variables are collected at certain sites and not others. And so your models have to be robust to a lot of the missing data that can appear. Finally, we're getting to the review process. So I think there has to be a balance between how much the urgency to communicate findings, as well as really polluting the literature with lots of stuff that isn't useful. And that's what we found in the systematic review. Is there was a lot of, there's a lot of grant money and a lot of time and effort gone into making these papers, that a lot of them are just completely useless to the community because they have so many biases in the way that they were written. And so it'd be very useful for the review process to appreciate, okay, yes, there's an urgency, but also we have to hold these standards within the machine learning community. And finally, I think it's important to really understand the line of sight to implementation in the clinic, having a clear vision for whether the algorithm actually could be regulated given the way that it's been developed, and how we would translate it into the clinic. And it's important to know that kind of early on. So in the future pandemic, we would now know this is the roadmap that we would have to follow to get this quickly regulated and into the clinic, and having that blueprint there. And that's everything. Thank you.
Thank you very much indeed, Michael. Fascinating and vast talk, as you were highlighting at the beginning. Congratulations to you and all the co-authors indeed. A mammoth piece of work. A quick question from one of the attendees on whether the images processed before this pandemic for healthcare would have suffered the same problems as what you have highlighted now. And also a related comment, highlighting, I believe that this was in particular relating to your slide on where you show duplication of the data sets, that in some way that shows a waste of resources in the middle of the pandemic, resultant perhaps from the rush. So,
yeah, so I think that for the first question, yeah, there's a lot of issues with these types of models from pre-pandemic as well. But this really highlighted it very, very urgently to us, where we were saying we want to use some existing models quickly, because developing a model from scratch is if we can use someone else's work, that would have been the best thing in the world, that we could have quickly taken a model and improved it. But we found that there were so many biases, and yeah, these existed pre-pandemic, and hopefully post-pandemic we can at least start to consider what is best practice when you're developing these types of models. And in particular, the best practice for developing a deep learning model using medical imaging. Best practice for data imputation is another area. Best practice for resolving this issue with incorporation bias as well.
And a quick question for me, or rather a thought: would you consider, so your study and like others discussed today really highlight the need for interdisciplinarity during the pandemic? So given especially the time pressure and also the type of the problem, given the vast uncertainty around what the problem was, and as you highlighted, you looked at the team that worked together with you on the research would have included specialists from different areas, even within healthcare, let's say. Yeah, would you think that there is really does the need forward, or would we go back after the pandemic and again focus on various areas?
I hope there's no going back from where we are now, because the way that we've learned so much from having radiologists, but then also cardiologists as well in the team from the clinical side, and really understanding an infectious disease specialists as well, and it really has augmented a lot of what we're thinking and added extra bits to the project that we were never thinking of before. So if we wanted to just focus on the chest imaging in particular, but then the cardiology people are saying, well, what about the heart? There's a lot of things that are important about the heart, and maybe that wouldn't have been appreciated without them. And I think they've been absolutely critical to getting the project, keeping the project going, and really identifying the right questions that we should be asking. Because we could develop a tool that's completely useless to them because it answers the wrong questions, or it's they have to use a separate workstation to use it, and they're not going to do that. So yeah, it's very important.
Thank you. Thank you again, Michael.